All right, what's going on, everybody? Today we're doing another LeetCode video. This one's called Binary Tree Level Order Traversal. So let's get into it. We're given the root of a binary tree. They want us to return the level order traversal of its nodes values from left to right, level by level. So basically, we're not really doing a search for anything specific here. We're just they do want us to search the tree in a specific way and then basically just return a data structure that reflects the tree being searched in that particular order. In this case, it's a level order traversal. So what does that mean? Let's just look at this example. So the level order traversal of this tree would be, going from left to right, level by level. We're going to return a 2D array. I mean, in C++, it's a vector of vectors, but what is that? It's just a 2D array. That's, automatically resizable under the hood. Nevertheless, so our first level is going to be this 3. So as you can see in that first nested array, there's only one value because there's only one node here in this first level. Okay, so we go to the next level, left to right again, 920. That's in a nested array. And then finally, the final and last level is 15.7 in another nested array. So it's all left to right, first level, second level, third level, so on and so forth. And then the nodes in those levels are also left to right. So yeah, basically we can also have a empty tree, so that edge case has to be counted for. We would just return an empty 2D array. So yeah, let's get into it. So the way I'm gonna do this is I'm going to use for our level order traversal, I'm gonna use a queue, and I'm gonna do an iterative traversal with a queue to do that level order traversal. So for our algorithm, basically the first thing we're gonna wanna do is push our root node to our queue. And basically with each outer iteration of our while loop, we're gonna be basically handling all of the nodes in the preceding level. We're gonna go level by level obviously for our level order traversal. So at first, again, we're gonna add this 3. Okay, now we can enter our, this is a queue. Now we can enter our loop. So the first thing we're going to want to do is basically get the the size of our previous level. So our previous level, right now we'd be looking at like this level, right? So, and the size of that is going to be 1. So level size. Let's record that as 1. It's important because that'll tell us we're going to be adding children potentially, but we need to maintain that level size so we know how many nodes to go through in our queue, pretty much. So the level size is 1. We're going to take this 3 from our queue, and we're basically going to pop it, but while keeping track of it with like a temporary node. So we have a temporary node pointed to this 3, right? We can pop it from our queue. So our queue at this point is going to be empty, and then we're going to push back our 3 to this new 1D array for our level. So let's push this 3 in there, and then we only need to iterate once, right? Because our level size is 1, and then we need to add the children. Basically, if this node has any children, we need to add that to the queue, and then we can push back the level. Once we've gone through all of the nodes at this level, we can push back that level to the result. But first we need to add those children. So there's a 4 and a 5 there. So we're going to do that left to right. And that's important. So we're going to have a 4, and then we're going to add a 5 to the queue. And this is not a stack, it is a queue, but I can just remember the order we're doing this in. So we're basically going to want to get to this 4 first because they were in line first, right? So yeah, that's pretty much it. For this first level, we do need to add this to the result array. So our result array is going to be 3 now, or a resulting 2D array rather. So now these are empty, and then we have this 4 and the 5 in the queue for the next iteration. So now we're going to be looking at this level, right? But I'm going to use this to point to whichever node we're looking at. So, but basically we're on the second level. We can see that our level size is going to be 2 because that's what we have in the queue. So 2. We're going to first look at this 4 because it was in the queue first. So we're going to pop that from our queue and have a pointer to it. So we're looking at this 4. Let's go ahead and get rid of that. So now we want to add the children to the stack. We also want to add it to the level, right? So let's add that 4. Okay, and we need to add its children to the queue, so 7 and 8. Let's go ahead and add those. Okay, and now we're gonna go through, we're gonna iterate again because we need to iterate twice because we know our level size was 2. So now we're gonna look at this 5. We're gonna go ahead and pop it from the queue. Okay, and we need to add that 5 to the current level, right? So let's add that after the 4. Okay, and then we need to add the children. So we have an 11 and a 14. Okay, so we're basically done iterating now for this level. We can add this level to our result. So we're gonna have a 3 and a 4 and a 5 basically for that next level. Okay, so we're done with this level, and then let's reset all of that. Okay, so we see our queue has a size 4 now, so we know our level size for the next level is going to be 4. Okay, so let's look at the 7. So we can pop that from the queue. So let's get rid of that. We can pop it from the queue. And we're gonna want to add that to our level. So let's go ahead and add the 7, and then we add the children, right? Which there are none. So we can just move to the 8. So now we're at the 8. Once again, this is pretty straightforward now at this point, since we've done it a couple times. We're gonna pop that 8 from the queue, just eliminate that, and we're gonna add it to our level. And then we just go on with the next number. We're iterating with the number of times that, with respect to, basically how many elements there were in our queue before we started, traversing those nodes and adding their children back to the queue, right? So 7, 8. So basically, we're going to just, kind of speed run through this end part. We're going to add a 11, and then a 14, and then just push that back to our result. Our queue is going to be empty once we're done with that, and we're going to be looping in our outer loop while the queue is not empty. So the queue is going to get empty, and we're going to be done with our algorithm. So 8, 11 for this test case. Okay, and then these are going to empty up again, and we just return this. So that reflects the level order traversal, right? Because we have a 3 in that first level, 4 and 5 in the next level, 7, 8, 11, 19 in that, or that's really a 14. But you get the idea. Just couldn't really see what I wrote there. But anyways, yeah. So that's basically going to be the step through for the level order traversal with a queue, iterative. So yeah, let's go through this code. So basically, the first things first, we need a data structure for our result. So let's declare a vector of integers, and I'll just call that result. It's completely empty because we have no idea how big the tree is at this point. We need to handle the edge case where the root could be null. So I'm just going to say, if not root, we're going to return res in its empty state. Okay, The next thing we want to do is declare a space for our queue. So we're going to initialize a queue here. Just in C++, it's just queue. It'll be a queue of tree nodes, and I'll just call that queue. And then we also need, we need to push the first node we need to push that root node, right? Because we've already checked if root is empty. So we know there's a root node at this point. We need to go ahead and push that to the queue. So we're going to push queue.push root. Okay, so at this point, we can go ahead and start looping. There's a couple other variables we can declare out here more globally to prevent repetitive declarations of variables. So one variable I'll declare is a temporary tree node pointer. So tree node star temp, basically for whatever node we're currently looking at. So it'll save up a little bit of time for reallocation. Let's make that null pointer at first, and then now we can start looping. So we're going to say while our queue is not empty, we're going to keep iterating. And then we also want, there's one more variable actually we can declare out here. We'll say we'll have an int for the level size, right? And then we'll just have that be, it doesn't really matter what it's set to because it's going to get updated to something with each iteration, but I'll just have that at 0 so we don't get any weird errors. Right, so the first thing we want to do is adjust that level size. So it's going to be whatever the current size of the queue is before we start doing anything for the outermost iteration. So queue.size for the level size. And then we're basically going to want to just iterate through all of those nodes in the previous level, right? So we're going to have a for loop. I'll just do seesaw for loop for an I equals 0 while I is less than that level size, I plus, so that'll just iterate level size number of times. And we also need a 1D vector for the current level. So I'll just say vector of integers called level. And then we're basically just going to, in this loop, we'll start handling each of those nodes from the tree. So I'm noticing this looks like a big gob of code and it's not very readable. So let's separate this a little bit. So this is our result array, and then we handle the edge case. This is our queue operations, and then this is just some variables that we don't want to redeclare a bunch of times. Anyways, okay, so now we're in here. We need to get a pointer, right, to the tree node that's at the front of the queue. So we're going to say, we already declared that out here, right, for our called temp. So we'll say temp is going to be equal to whatever's at the front of the queue. Okay, now that we have a pointer to that, we can just pop it. So we'll say queue.pop. Okay, now we can add it to the 1D array, that is the current level. So we'll just say level dot push back, level.push back, and then whatever that node value is. So we'll say temp value, and then we can, at this point, we can add the children, right? But the children could be, let me just clean up this code a little bit. The children could be null, and we obviously don't want to add null children, right? So to account for that, let's just go ahead and do an if statement. So if temp left, because we want to do left to right to match the way the formatting they showed us. So if temp left, we just want to basically push that left child into the queue, right? So we'll say queue.push temp left, granted that it exists. And then we're going to do the same thing for the right child. Oops, to Command C there. So same thing for the right child. And then basically after that, we should have this level fully populated. So once we exit this for loop, we can just say result dot pushback level, right? To just add that to the result. And then at the very end of this, we can just return result. Okay, so assuming I didn't make any bugs here, this should be the complete code, and I'll just see if it runs, then we can go over the time and space complexity. So yeah, so this is the full code, and let's go over the time and space complexity. So in terms of the time complexity for this problem, we're gonna be running at big O of n time, right? Because where n is the total number of nodes in the tree. Basically because we have to visit every single node. We're not really doing any backtracking or anything like that, so it is going to just be linear with respect to the total number of nodes in the tree. In terms of the space complexity, it's going to be big O of, you could potentially have, because really the only, so obviously we have a vector for a 1D vector for the current level, and then a 2D vector for the result array, which those are never going to grow bigger than n. And technically we have to have those, so like I wouldn't even really count those as extra space, but I would count the queue as extra space. But you're never going to have more than big O of n nodes in your queue, like regardless of how the tree is you know, set up, like if it's like super skewed or there's a big level or something, you're never going to have more than big O of n nodes in your, you're never going to have more than n nodes basically in your queue at any given moment. So we'll say big O of n space as well for this, for the space complexity, just for that queue. So yeah, hopefully this video helped you understand this problem better. If it did, please leave a like and subscribe, and I'll see you guys in the next. Peace.